So we're going to be looking a bit at now using resultant forces and using that to tell us about the acceleration of an object and vice versa, being able to know about the acceleration of an object and then deduce the forces that are acting on it. So the first thing we need to know, which some of you may already know, a sort of fundamental law of the universe, and famously stated by Isaac Newton, is this particular equation here: F equals ma. Okay, force equals mass times acceleration. And I think it's probably worth to just clarify really precisely what each of these letters is actually referring to. So the idea is you've got an object has mass, an object has a resultant force on it at all times. That resultant force may be zero, but if it has no force, we call the resultant force zero. Otherwise, it has a resultant force which is non-zero. And additionally, all objects have an acceleration. Either that acceleration is zero or it's non-zero. But for each three of these letters, they're referring to, in the case of F, the force, the resultant force, M being the mass, and A the acceleration, all referring to the same object. So let's be very clear here. The F is specifically referring to resultant force. Okay, so there's only ever one resultant force acting on an object, and that resultant force is the sum of all forces that may be acting on it. Okay, so even if there are many forces, then you just combine them into a single resultant force. Okay, so there we go. So we've got the resultant force measured in newtons, mass measured in kilograms, and the acceleration of an object measured in meters per second squared, so that's to the -2. Okay, and this is what we're effectively going to be using to relate force and acceleration for a given object. So an insanely simple example, let's just quickly do it though, just to confirm we know what's going on. So the acceleration, when a particle of mass 1.5 kilograms is acted on by a resultant force of 6, super simple, m equals 1.5, resultant force F equals 6. We know that F equals ma. This implies that the acceleration must be equal to F over m equals, in this case, 6 over 1.5 equals 4. And if we want to put the units, we can say meters per second squared. Okay, so now I'd just like to talk a bit about notation in terms of our diagrams when we're trying to indicate acceleration. So let's say I've got a body, so some sort of object, and I've got two forces acting on it. So let's just make some up. Let's say I've got a force acting that way, and perhaps there's another force. Oh, let's try and do that a bit more straight. Let's have another force acting, say, like this. Okay, and then might as well, let's just put the resultant force on here as well. So again, if I grab these two arrows, I should be able to work out what the resultant force is geometrically. Oh, it's just about a horizontal line. That's just coincidence. There we go. There's the resultant force. So in fact, we can now delete the less relevant parts there. Okay, so there's the resultant force. Let's stick it on there. Okay, so the blue arrow shows the way the object will actually move. So in this case, we've got this yellow box is going to move to the right according to that blue force. Now, we said that F equals ma, right? Now, the important thing about F equals ma, there it is that technically, I say technically, I mean this is precisely what F equals ma is telling us. A is a vector and F is also a vector, right? So I've just marked that up here with a little vector notation, right? M is not a vector. M is just mass. which is a scalar quantity. So really what's going on here is we're saying the force is the same direction as the acceleration, and the magnitude of the force is the magnitude of the acceleration times the mass. Okay, but their direction is the same, because remember, if you multiply a vector A by a scalar m, you're not going to change the direction, you're only changing the magnitude. So if we go back here, if this resultant force, this blue arrow is the resultant force, then that means the acceleration is going to be going in the same direction, right? So let's just mark that on the diagram now. In fact, I'm just going to drag this blue arrow away. Okay, so that blue arrow, roughly speaking, represents the acceleration, right? At the very least, the direction of the acceleration. And the way we're going to mark that in the diagram is by adding a second head, right, to the arrow. So this double head notation of the arrow, this means it's an acceleration. So the way you can see this picture now, this is a fairly sort of typical example of a force diagram, where you'll have the body, you'll have some forces acting on the body, in this case these two red forces. Usually they'll be labelled with a magnitude, or perhaps a letter, some variable which needs to be found. And if you're given the acceleration, it'll be given in the form like this, a double-headed arrow, where the direction of the arrow, or the direction of the double-headed arrow, shows you the way in which the acceleration is moving. Okay, and just remember that the acceleration necessarily will be in exactly the same direction as the resultant force. Okay, the only thing we don't know yet is the magnitude. The magnitude of this acceleration we don't know. Why? Because we don't know what the mass is, right? We don't know what the mass of the object is. If it was 1 kilogram, then this 1 kilogram mass would have an acceleration which is exactly the same magnitude as the resultant force. If it was a 2 kilogram mass, then the acceleration would be half as much, right? So now think about that. Okay, if you've got F equals ma, right, F equals ma, if the resultant force is not changing and I increase the mass, say double it from 1 kilogram to 2, then the acceleration is going to halve, right? It's going to go from whatever it was to half that amount. Okay, so just remember that increasing mass decreases acceleration by the same multiple, right, and vice versa, right? Which makes some sense, right? If you imagine a heavy object and you're pushing it, it's not going to be moving as quickly. Its velocity is not going to be changing as quickly as that of a light object. If I push a less massive object, right, with less kilograms, if I push that with the same force, it's going to move a lot faster, right? It's easier to move light things than it is to move heavy things, and that relates to the fact that the acceleration and the mass, if one increases, the other decreases, at least if the resultant force stays the same. Okay, so let's look at an example now. Now, the only slightly annoying thing about, well, not annoying, but the realistic thing about these examples is, going back slightly on what I said a moment ago, the magnitude of the arrows not really relevant in these diagrams. Okay, so oftentimes in force diagrams, the magnitude of the arrow won't actually be drawn to scale, because if you've labelled it with a number, then there's no need to go by the actual magnitude of the arrow itself. So, for example, here you've got an 80 newtons arrow, here you've got a 20. Now in this case, I mean, you could probably say the 20 newtons arrow is about a quarter the size of the 80, but you can't by that logic necessarily say, well, because this X arrow looks about the same length as this one, therefore that's also 80 newtons going to the right. Unfortunately, you can't just go by the size of the arrows. They're not necessarily to scale, not by default anyway. The directions of the arrows, though, always important. The direction of the arrow is important. Okay, so let's look at A then. Okay, so the idea is you've got 4 forces on this object, okay, and then you've been told this acceleration. Now the thing about this acceleration is that it's going horizontally and it's going to the right. So what that means is there's absolutely no vertical acceleration, right? The acceleration is only going horizontally. Now, if that's the case, if the acceleration is horizontal, that means there's no vertical acceleration, right? So perhaps let's just write this down formally, okay? So if I resolve vertically, okay, so that's me, I'm doing an up arrow in brackets to indicate that I'm resolving vertically now. The force, okay, the force vertically, so taking up as positive, well, we've got a capital Y going up, and we've got 2g going down, okay, 2g going down. Let's just make a note. G in this case is referring to the value 9.8, okay, that's acceleration due to gravity. I think we'll come on to that in a moment actually, but for now it's fine. As long as you know it's that value, then that's fine. Okay, so you've got y going up, 2g going down. Because the 2g is going down, we call it negative. Okay, that's the force. And the acceleration in this case, vertically, is 0. Okay, there's no vertical acceleration. Therefore, if we equate the two, y minus 2g equals 0, then you just get straight out of that y equals 2g. Okay, which should be obvious really, because if you think about it, if I've got a force going up here y and a force going down here 2g, and the overall acceleration is 0, if acceleration is 0, resultant force must be 0, and therefore they're equal. Okay, so therefore y must be equal to 2g. Okay, so that's that bit done. Then if we resolve horizontally, so using the right arrow, what forces have we got? Well, you've got x going to the right and you've got 4 going to the left. Okay, so that's x minus 4. Okay, because the 4 is going left, so it's a minus. And the acceleration in this case is equal to 2. Okay. Now I just pause there for a second because I've realised something that I glossed over slightly in the upward direction. Okay, so I cheated a bit here. I said acceleration equals 0, and then I equated these. Now, I didn't actually make use of the mass, but of course, so let's just go back there for a moment. If I have F equals ma, and a is 0, then in that case, you can just say F equals 0. So, in other words, the acceleration and the force are in fact the same thing, okay? But that will only work when a is 0. So we can't necessarily do that in this case here, okay? So we've got F equals x minus 4, a equals 2. The mass is equal to 2 as well. So putting that into F equals ma, we end up with x minus 4 equals m times a, 2 times 2, so we get 4. And that therefore implies that x equals 8. And then just one thing to finish off actually, we said here y equals 2g. We didn't really fully answer the question, so that's 2 times 9.8. That's equal to then 19.6. Okay, so we've got 19.6 newtons for y and 8 newtons for x. So I'm just going to rub that out, and we'll take a look at part B then. Okay. So for part B, let's just shortcut this slightly for the vertical case. Sorry. So for the vertical case, okay. Again, you've got 0 acceleration. So if you've got 0 acceleration, then that means all the forces going up are going to be the same as the forces going down. Okay, so we don't really need to use F equals ma, at least not explicitly. We can just use the fact that the forces must balance. But that's only because the vertical acceleration is 0. So let's look at all the forces going up. We've got Y, that's going up, and all the forces going down. Well, we've got this 20 going down and this 4G going down. So therefore, we're going to take away 20, we're going to take away 4G, and we know that that resultant, taking it only in the vertical direction, must be equal to 0. Okay, and therefore Y equals 20 plus 4G equals 20 plus 4 times 9.8. Okay, equals and then whatever that is. In this case, would be 59.2. I'll just check that quickly. 59.2. Okay, and then for the horizontal case, so let me just make some space. For the horizontal case, we've got, again, taking right as positive this time, horizontally. So what forces have we got going on? We've got X going to the right, we've got 80 going to the left. So that's my F, that's my resultant force. My mass is 4. My acceleration, okay, and then we've got to be a bit careful here. What is acceleration? If I'm taking right as positive and it's 2 meters per second squared going left, then that means acceleration must be -2 because it's going to the left. Okay, acceleration equals -2. So put all that together and we end up with x minus 80 equals m times a minus a, and that implies that x is equal to 72. So then something I probably should have mentioned slightly earlier, let's just clarify on this this thing g equals 9.8. Okay, so in case we're unfamiliar, this value is effectively the acceleration that any object on the surface of Earth will experience when it's near the surface of Earth, okay, due to gravity. So if we just draw this diagrammatically, if I've got the ground and let's say I've got some sort of object, okay, I've got some nice little red ball here or something, then if I wanted to draw the acceleration it was experiencing, in this case the acceleration is going to be downwards, and it's going to be a value of 9.8. okay, and that's what g is. That's effectively what we mean by g. So when we talk about g, we're talking about the acceleration that something experiences due to gravity. So then if we think about the weight of an object, in fact, let me just go back to that little drawing I had and just take this across. Okay, so if we've got this situation going on, okay, let's just quickly apply F equals ma in this scenario. So we've got, let's take down as positive for a moment, okay. So resolving vertically, we've got the acceleration is just g, okay, 9.81. Then the force, okay, the force that's acting on this object, okay, that's the weight, remember, okay. Now that force is caused by gravity, but the force itself we call the weight, and the acceleration that it will experience is 9.8, okay, and that you can take as a given. So now if we say, okay, let's say this object has a mass of m, okay, that's its mass. If we have F equals ma, then that means we can say, okay, the weight is equal to the mass times the acceleration is g, right? So F equals ma directly gives us the fact that the weight of any object is just mass times g, all right, or at least the weight of an object near the surface of the Earth. Okay, if you're talking about the weight of an object on a different planet or on the moon or something like that, then this g will be different, right? But this is why we confuse weight and mass so often, because this g value, for most practical purposes and in your daily lives, this g never changes. It's always 9.8. So therefore weight and mass are directly proportional to each other at all times, just by this factor of 9.8. Okay, but if you have any force diagram and you're told the mass of it, let's say it's 2 kilograms, then if you want to label the force of weight, then you'll label it as 2g. Yeah, or if it has a mass of 5 kilograms, you'll label it as having a weight of 5g. Okay, that will be the force you label it with, 5g. So that explains why in these previous, let's just take a look at this again. In these diagrams here, this 4g is because it had a mass of 4 kilograms, and this 2g here is because it had a mass of 2 kilograms. Okay, hopefully that makes sense. Right, so let's look at a final example before I give you some questions to do. So, as will be the case in a lot of mechanics sorts of questions, you want to start getting used to drawing a diagram of what's going on. Right. So we have here a body of mass 5 kilograms is pulled along a rough horizontal table. So I've already drawn a green line for the table. So then this body, I mean, by body, it doesn't literally mean like a body of someone, it's just an object, right? So let's draw this body. It has mass 5 kilograms. So immediately what we can do is draw on the weight. Okay, the weight force. So if it's 5 kilograms, then its weight is 5 times g, which is 9.8. And it's pulled along a rough horizontal table. So the fact that it's rough, that's just telling you that there's going to be a frictional force opposing the pulling motion, right? It's pulled along a rough horizontal table by a horizontal force of magnitude 20 newtons. Okay, so it's got a force of 20 newtons pulling it this way, and a friction force of magnitude 4 newtons. Okay, so as we said, this table is rough, so that means as it's being pulled along to the right, then the friction of the table on the body is making it slow down a little bit in some sense. It's resisting this motion of 20 newtons, so that's going in the other direction. Okay, so let's draw that on here. So that is 4 newtons to the left. Okay, and then as I said before, in this case, arrows are not to scale. My 20 arrow and my 4 arrow are almost similar in length, but that's not really the point. The point is that the directions are opposite to each other. The direction is what matters in this case. So 20 to the right, 4 to the left, 5g down. Have we got anything else going on? Not in terms of forces, no. So now we can start considering the question itself. Okay, so it's asked us to find what is the acceleration of the body. Okay, there is one force we've miffed off. Okay, so it's on a table, right? And it's not falling through the table, clearly, because the table is solid. So the fact that you've got 5g going down means that there must be another force that's preventing it from falling through the table. So that's the one we've missed off here, actually. Okay, so there's actually going to be another force of 5g pushing it up. Okay, in fact, let's just label all these forces briefly, actually, before we continue the question. So that 5g, that's the weight. Okay, this 5g going up, this is the normal reaction. And in fact, we've basically just answered part C there. That's the normal reaction. The force of 20 newtons, I mean, it's being generated by pulling. So because you're pulling it, I would probably call that a tension. Okay, so it's probably being pulled by a string or something. So there's some tension pulling along that object. And then you've got this other force, friction, okay, taking it to the left. Okay, right, so now that's our complete force diagram. So if we now look at part A, as we were going to, so we're looking for the acceleration. The acceleration, as would make sense, it's only going to be horizontal, right? Because the object stays on the table, it's not moving up or down, it's only moving left or right. In this case, you can probably tell it's going to be moving to the right, because a force of 20 is greater than the opposing force of 4. So let's resolve horizontally. Let's write it here. So going to the right, what's the resultant force going to the right? Well, it's just going to be 20 minus 4, isn't it? 16. That's the resultant force if we're only looking in the right horizontal component. And then MA, in this case, M is 5, isn't it? And A is the thing we want to find. So if we equate those two, 5A equals 16, you therefore get that your acceleration is 16 over 5, or in other words, 3.2. Okay, and we've only really got part B left now, because C, if we just skip ahead to that, it says the magnitude of the normal reaction between the body and the table. I mean, we've labelled that immediately because it's just so obvious, really. You've got this object sitting on a table, it's not falling through. The normal reaction must be equal to the weight, so that the vertical resultant force is 0, because it can't be accelerating up or down because it's not moving up or down. So C we've basically done. So if you want to finish part B, to be honest, now we're just straight back to Suvat equations, because the main new part of this question is A, is finding the acceleration. We might as well quickly finish it though. For part B, we have now that the acceleration equals 3.2. Okay. The distance travelled by the body in the first 4 seconds, so therefore t equals 4. What else do we know? Right, so there's this part of the question here where it says, given that the body is initially at rest. Now that part of the question is completely irrelevant for part A. The acceleration of the body, it doesn't matter what its initial speed was. The point is what are the forces on it now. But for part B, that's when this becomes relevant. The body is initially at rest. So now we've got initially at rest, therefore u equals 0. U equals 0, and what are we trying to find? The distance. Okay, so s equals question mark. Okay, so we're just doing our usual. S equals ut plus a half at squared. Okay, is equal to, well, u is 0, so that's nice, so it just becomes half at squared in this case, which is going to be a half times 3.2 times 4 squared, and if you work that out, comes to 25.6 meters in this case. Okay, so B is just Suvat really, using the acceleration you've already been given. So it's your turn now, time to look at some questions. This first one is, I mean, calculation-wise, it's extremely simple, but it's just something to think about. You want to be using the fact that weight equals mass times this constant g. Just have a think about it. Pause the video now and see how you get on. Okay, and the answer to that is just 1.6 meters per second squared. So this is where you get the fact that oh, what actually was it? It says, yeah, so this is where you get the fact that the gravitational pull on the moon is roughly 1/6 of what it is on the Earth. Okay, so I mean, you've just been told that experimentally there, that you know, you're 735 newtons on Earth, 120 newtons on the moon. The weight changes, the mass is the same though. So if you wanted to find the mass of the astronaut, you'd just have to do 735 divided by 9.8 and you'd get their mass, which would be what more commonly we'd refer to as weight. But technically speaking, that's not really their weight, that's their mass. Right, let's look at the next question. In this one, all you're doing is use F equals ma, find resultant forces, or potentially find, yeah, so you're given the acceleration, you're given the mass, find the resultant force, find the missing value. Give that a go, pause the video now. Okay, and there's your answer to A. And you've also got there your answer to B. So for this question, just give it a go yourself if you want to. I'll give you a brief hint, but if you don't want the hint, just try it first and pause the video now. Okay, and then if you do want the hint, then it would be to use the SUVAT equations for 10A. So just use your usual SUVAT to find the acceleration. Okay, so you're not using F equals ma for part A, as far as I can tell, just SUVAT. Then you can use F equals ma for part B. Okay, so let's look at the answers. There we go, 0.5 meters per second squared, and the tension is 45 newtons. And final question, if you don't want the hint, have a go, pause the video now. Okay, and if you do need a hint, you're effectively going to use F equals ma, so that is the force is that 200 newtons. Use F equals ma then to find out what the acceleration is on the van, or in this case the deceleration. Once you've found the acceleration equals F equals ma, using F equals ma, then use your SUVAT equations, both for part A and for part B. Give that a go. Okay, and then you've got your answers here.